In this 10th lecture on Lagrangian mechanics, today we shall derive the Lagrangian of a relativistic particle. Before going to relativity, we first give a brief introduction, very brief introduction of tensor and which will be required in our subsequent discussion. A tensor is a quantity or a set of quantity which is defined under coordinate transformation. It's in a three-dimensional space or in a three-dimensional space, a set of quantities AI which is defined as del x bar, del xi a bar alpha, where the repeated index means there is a sum over alpha from ranging from I to 3 for three-dimensional space and from I to n for n-dimensional space. For three-dimensional case, there are three such quantities a1, a2, a3 and a bar alpha 1, a bar alpha 2, a bar alpha 3, and for n-dimensional case, each of them has n quantities. The A represents the same physical quantity. It represents the components of the quantity A as seen in S prime, and A bar are the components of the same quantity when viewed in S bar prime. If the relation between the components of the quantity A is of this form, then it is called a covariant tensor of rank. Tensor of rank 1, or it is called a covariant vector. Similarly, if we have a set of quantities AI which is given by it should be alpha, it should be in the subscript. This is called contravariant factor contravariant tensor of rank 1 or a contravariant factor. A covariant vector of rank 2 a covariant vector of rank 2 is defined as Aij is equal to A bar this is so in three-dimensional case there are 9 such quantities, and in n-dimensional case there are n square such quantities. So it is a covariant tensor of rank 2. Similarly, contravariant tensor of rank 2 is defined as this is a contravariant tensor of rank 2. And a mixed tensor of rank 2 is defined as this is a mixed tensor of rank 2 whose covariant rank is 1, contravariant rank is also 1. It it is a mixed tensor of rank 2. Now, if we in general multiply two tensor, one of rank n, another of rank m, then the resulting quantity is generally a tensor of rank n plus m. But if some covariant, say we have two vector A which is I, J, K, L, it is a tensor of rank 5, whose contravariant rank is 3 and covariant rank is 2. When it is multiplied by another vector, another tensor, say like this. KLM PQRS, then it is a tensor of rank 5 and it is a tensor of rank 4. So the resulting quantity is a tensor of rank 9. So the resulting quantity will be a tensor of rank 9, which is KLM PQIJRS. This is the component. But if some of the covariant rank matches with the contravariant rank of other, say what happens to this? I define KLM IJ, and this B vector is, B tensor is IP, and K RK. Then a covariant rank of A tensor matches with the contravariant rank of B tensor, and then contravariant rank of A tensor matches with the covariant rank of B tensor. So the resulting quantity will be a tensor LMP, and this is JR. So it is a tensor of rank 5. So this 5 is actually, it was a tensor of rank 2, as a covariant index is same, so my rank is reduced by 2. Another pair is matching, so the range is 5. So we define the norm in this notation. If we want to define the norm of a vector, then the norm of a vector is defined as say vector A. If we define, so norm of vector A modulus square, or simply A square, is defined as AI. A sum over I is implied over all possible I values. We are employing Einstein's summation convention. So whenever there is a dummy in the repetition of dummy index, then sum over it is implied. As for example, here the sum over alpha is implied, here also alpha, here the sum is over alpha beta is implied. So if we now go to relativity, in one more thing to be defined. A scalar is a quantity which do not undergo any change under coordinate transformation. In terms of the tensor, it is the definition of tensor, or it is a tensor of rank 0. So in general, in our earlier classes, we used to write a vector as like this: ay k cap az, and we used to say that ax, ay, az are scalars. No, ax, ay, az, they are not scalar, because as we change the coordinate system from one coordinate system to another one, ax, ay, az undergoes a change. But as for tensorial definition, a scalar is one which does not undergo any change. So in that sense, the components of a vector are not scalar, they are just a component of a vector. uh, we If we go to the special theory of relativity, then we define a 4 vector. A 4 vector is one which is a vector of having 4 components in the 4-dimensional Minkowski space, such that they transform from one inertial frame to another inertial frame via a Lorentz transformation. And if we define the components of the vector as A0, it is the norm of the 4 vector, and this is a Lorentz scalar. So it is a Lorentz scalar, which is the norm of the 4 vector. It is a Lorentz scalar. That means under Lorentz transformation, if we transform from S frame to S bar frame, the corresponding quantity would be A bar 0 minus A bar 1, A bar 2, this is not square 2, but this is the mod of A bar square, and they are same. So this is the definition of Lorentz scalar. As for example, the space-time interval, c square t square minus x square minus y square minus z square is equal to c square t prime square minus x prime square minus y prime square minus z prime square. They are the same. So this is a space-time interval is a Lorentz scalar. And another thing, if we divide a Lorentz scalar, say Lorentz scalar is S, and if we divide it by a contravariant, differentiate it with respect to contravariant quantity, the resulting quantity will be the covariant quantity. And if we could differentiate it with respect to covariant, then we get a contravariant component. With this small introduction to tensor, we now switch over to our main purpose, that is to obtain the Lagrangian of a relativistic particle. In classical non-relativistic mechanics, we obtain Lagrangian as a scalar because it is the subtract t minus v, where both t and v are scalars, rather they are Galilean scalars. Or three, so no, I should not say Galilean scalar, they are the 3 scalars because time was not there. In relativity, so in 3D that we are dealing till now, we define the Lagrangian as xi dot and t. If we want to define it in 4-dimensional Minkowski space, we should write Lagrangian L, which is, and it is the proper time, tau is the proper time, and this should be a Lorentz scalar. Furthermore, as beta tends to 0, beta means beta is equal to v by c tends to 0, the classical limit will be approached. classical limit will be opposed. These are the primary idea that we have from beforehand. So we say that whenever we use the four-dimensional Minkowski space, we use the, for position coordinate, we like the xi, velocity components pi, and time is proper time, so that the Hamilton's principle in this case, it looks like xi vi tau integrated over tau. This is 0. Following the standard prescription of Euler-Lagrange equation, we get ddt del L del vi minus del L del xi is equal to 0, which is the Euler-Lagrange equation in its covariant form, and we further define the momentum pi is equal to del L del vi. Here M is the Lorentz scalar, and we have differentiated with respect to a contravariant component of velocity, so it is the covariant component of the momentum. Obviously, these are the four momentums. Now, these are the primary ideas that we have. Now, in relativity, we define the covariant momentum as mvi. So, there are two definitions of momentum, one from Lagrangian point of view and other one from Newtonian point of view. We use these two relations to find out L. So our starting point is Pi is equal to del L del Vi is equal to Vi. Just note the change in covariant and contravariant components. Furthermore, we write M is equal to M0 1 minus beta squared to the power of Vi, as a moving mass is equal to M0 1 minus beta squared. This is being utilized. If we integrate this, on integrating we get L is equal to integration M0 1 minus beta square 1 minus beta square to the power minus half pi dvi, apart from a constant. There is a constant. We define z square equal to 1 minus beta square. So 1 minus beta square is 1 minus 1 by c square v square. In terms of tension notation, this is 1 minus c square vi. So z dz, if we take the differential 1 by c square here dvi, we could also write it minus c square vi dvi, but this form should show this. So this relation together with this becomes M is equal to vi dvi, so this is z dz minus M0 is a scalar, so taken out, c square is a scalar, constant is taken out, so this is for this v dv is equal to z dz yz, so this is minus M0 c square integration over dz, so this is equal to M0 c square, and for z we write 1 minus beta square to the power half. So this is the Lagrangian for a relativistic particle. So let me check whether the basic two requirements are being satisfied or not. The quantities involved, m0, the rest mass, is a Lorentz scalar, c square is a Lorentz scalar, this quantity is a Lorentz scalar, so product of three Lorentz scalar is again a Lorentz scalar, so L is indeed a Lorentz scalar. Now, what happens to L in the limit beta tends to 0? Beta tends to 0, this becomes minus m0 c square, and then we expand 1 minus beta square into binomial series, keeping the up to first order term plus higher order terms. So this approximately equal to minus m0 c square 1 minus half v square by c square. So this is minus m0 c square plus half mv square. So we haven't considered the kind of potential energy till now. So this gives us the correct classical limit of the relativistic Lagrangian. If we want to write the Lagrangian of a particle subjected to a conservative force field, then it is m0 c square 1 minus beta square to the power half plus b. This is another way of getting this expression for alternative way of getting the Lagrangian, of getting L, let us say. Now the Hamiltonian. I haven't yet introduced yourself what Hamiltonian, but you must have some idea about the Hamiltonian. In non-relativistic mechanics, Hamiltonian is defined as qk dot pk minus L. In non-relativistic mechanics, it is a three scalar. So in relativity, we should write H as summation over I. We are using Einstein's convention. So in this convention, this reads as. So this is Pi minus L. So this is to make the quantity scalar, we have used the product as covariant, the mixture of covariant and contravariant. This part we can write Vi m Vi minus L. So this is m v square minus L. And H, for a conservative system, H is the total energy. So H is equal to, we write mc square and the energy of a particle as per relativistic theory. Or L is equal to, or rather minus L is equal to mc square minus mv square. If we take m common, this is c square minus v square, which can be written as m0 1 minus beta square to the power half. This is for m, and taking c square common, this is 1 minus beta square. So altogether this is m0 c square 1 minus beta square to the power half. The same expression for the Lagrangian. If we introduce the relativistic particle in electromagnetic field, then momentum will undergo a change and the Lagrangian will take a complicated shape. I am not going to this. This is a simple, we keep our discussion to this simple level. So we have found the Lagrangian of a free particle or a Lagrangian of a relativistic particle. And a special case may appear that the Lagrangian for light quanta. For light quanta, we know it is a relativistic particle with zero rest mass, and we can get the Lagrangian or Hamiltonian for a light quanta.